So today we are going to talk about register allocation, and I will first just describe why we are doing register allocation and go through multiple steps. First, creating webs. That means a unit that gets a single register allocated. Then interference graphs and register coloring to make sure that there are enough registers and registers doesn't interfere with each other. And up to that, at that point you can, and spilling, and at that point you can actually do a basic register allocator. Then I will talk about a little bit more optimization about splitting, live range splitting, and other optimizations to improve register allocation. So why are we doing this? We basically want to store value between a definition and a use. So what happens is program compute values, and at the value definition point, we are something get assigned to a left-hand side, and then some uses of the values later that reads those values. And we have two choices, okay, between def and definition and use. The first choice is to store everything in memory. That's what you guys are doing right now, and retrieve from memory for each use. If you are doing a RISC architecture, this is a pain because there was not a single operation. You can do ALU operations on memory, so you actually load it into a register, operate, and store. In x86, it's not that much of a pain because you can do some operations basically directly from memory, load, do some operations, but the operations are limited. You can't load two from different memory locations, operate, and store. So whereas register, you can do a little bit more. So second option is store the values on registers and operate on the value from registers. So why is this very important? Because register allocation have a very direct impact on performance. More than any optimization you guys did, this probably have the highest impact because it affects almost every statement of the program. Because every statement you're dealing with values. You are taking some values, doing some operations, storing values. And the thing about that is what happens is if things are in registers, it eliminates some very expensive memory operations. Memory have two issues. One is there's a latency. That means you have to actually go to the cache, actually get the thing, and if it is not in the cache, get it from memory. It's multiple cycles to get it. Second, there's a bandwidth issue. Because something like x86 64, you can have multiple operations in flight. Multiple operations can happen in the same cycle. There are many ports or accesses to the register file. You can get, I think, about 6-7 items or more probably even out of the register file in a given cycle. Whereas in a memory, normally you have about 2 ports. You can only get 2 items or write 2 items into memory. So because of that, if you have too many memory operations, you actually really slowing down because you don't have enough bandwidth to keep doing that. And also the other thing is there are only limited number of memory to memory ALU operations. You can't do 2 memory in this. It has to be register to memory or memory to register type operations. So because of that, sometimes if you want to add 2 items in, add one value in memory to another value, you have to probably load it to register and then add it to that value. So you have it, whereas if it's in register, I can just do it in one operation. So there are limitations in there. And I think because of that, this probably give you the biggest bang for the buck in any optimizations you do. So what can you put in a register? So any compiler generated temporary. This is why we said keep it as a temporary, compiler generated temporary, keep it separate so you can just figure out in the register allocation how to put it there. There are a lot of language level values also you can put. So there are some local scalar variables. Any constant sometimes can put into register. If you keep reusing the constant again and again, there might be opportunity to do that. Values stored on array elements. So if you have elements in some kind of array or structure, you can store it in register. There you have to be a little bit careful whether you can take it out of memory, whether they're aliasing. I don't think you have to worry about it that much. But it's not as simple as just a simple scalar. Because now we have 2 locations in there because in a scalar, like for example, compiler generated temporary, there's no assigned location for that. But the minute you start actually having objects, there's a memory location, and now the thing is in 2 places, and you have to make sure that it stays consistent. Other thing that in a normal machine you have to worry about, here it's not that much of a, you don't have to worry about, is different data types have different registers. So, for example, floating point has its own registers, integers have its own registers. If in modern machines, if you do these SIMD type small operations, they have their own set of registers. So, whereas memory is one gigantic big blob, whereas registers, you have different groups. So, it's not like you can assign a floating point to integer registers and use that directly. So, you have to know which registers you go into. So, I think one of the benefits I mentioned is fewer instructions in there, and registers are faster, and I mentioned these two facts. But the key thing is there's only small amount of registers. Memory is basically, for anything you consider, it's unlimited. As far as compile is concerned, memory is unlimited. We just write to gigantic memory and let the hardware deal with, if there's not enough memory, it will swap it out, whatever. Whereas registers, there's a very limited set of registers. In x86 64 and x86 it's even harder, because normally these days a lot of machines have large number of registers, but x86 normally has a very small amount of registers. And whereas something like if you go to Itanium, there are 128 registers. And also the worst thing, some of those registers already have pre-assigned meanings. So you can't just keep using stack pointer or frame pointer, they have pre-assigned meanings. So what you have to play with is even a smaller number. And sometimes some of those registers have some very specific values. For example, if you are doing a divide, the data has to be in a certain register. And at that point, you have to make sure that those constraints are satisfied. So since x86 is a CISC architecture, there are a lot of these weird conditions that you have to deal with when dealing with registers. So that just set the base for what we are trying to do. And now let's go on and start looking into how to do register allocation. So the first concept I want to talk about is webs. So what we are doing is, what we are in this class is web-based register allocation. So what we do in register allocation, the entire steps is, first we determine live ranges for each value. So what that means is each value has to get in there, and what's the range that value has to be, and which accesses can be grouped together, what we call a web. And then if you have multiple webs, we have to figure out what are the overlapping webs. So if two ranges are active at the same time, they are overlapping and they can't go into the same register. So you have to look at that interference. And then at some point, if you don't have enough registers, you have to deal with things like spell cost. You have to figure out, okay, now I don't have enough registers. I have to spill something into memory, and what's the right one to spill? And there's a lot of heuristics around this thing. And then finally, decide which webs to get a register. So you have to allocate, and then you can do a bunch of optimizations. If you have to spill, say instead of spilling, can I split the web and do some interesting things to actually make still allocate registers? Then everything gets spilled. And finally, you assign to hard registers. So you know, okay, so I know these things get registers, but which registers? And you can do it intelligently. And then you have to generate spill code. And that's basically about the process you have to go through. This split webs is optional. You don't really have to do that, but the rest basically you have to follow through. So webs. So the starting point of a web is a diffuse chain. So did you do, I guess you guys build diffuse chains for data flow optimization? Did you figure out? Do you know data flow to do find diffuse, basically given each use, figure out where all the definitions are, and vice versa, use def and diffuse chain. So what it does is connects definitions to all reachable users. So what you want to do is entire thing in diffuse put into a single web. You can probably formulate this as a nice data flow problem. I think this is a good way to go and do that. So what that means is defs for all reachable users must be in the same web. So if you have a definition, all the places that definition is used have to be in the same web. The same way, if you have use, all the def that reach this use has to be in the same web. Okay, because that is the thing that I get register allocated. And you can use a simple union find type algorithm to go and do that. And you can look at your algorithms book, find union type algorithm, and that will nicely help you do that. So here's a simple example. So what are my webs in here? Anybody want to tell me what's a web?
The smallest one is
This one, because I have a def and I have a use, these two. This is not in the web, because this is the def actually going to get read. So these are, these two are in the web, because I have def and I have use y. Is this in that web? No, because this def doesn't reach there, and these two are in there. Okay, those two are very clear. There's def and there's use, and that's directly in there. How about here? I do a def y and I do use y. This is in a web. What happened to these four?
they're all
Why?
because the left apex can reach either use and the right use can be reached by either def.
Yeah. So basically what happens is you can use this def reaches these two users and this def user reaches this use. So basically unified algorithm will basically tell us this entire thing is in one web. So in this program I have basically 4 webs that comes out. So first thing is look at each function, figure out all the webs in there. So basically web is basically unit of register allocation. So if you allocate a register for that web and the entire operations within that web take that register. And so web can get either register or web can be allocated to memory. So if this web is in the memory, all the operations happen from memory. However, you probably will have to keep probably one scratch register, because assume I am doing operation with two things that's already, 2 webs that's in the memory, and you can't do that direct operation directly. So you need to have a scratch register to bring that value to the operation and save. So one scratch register will probably do that. So you need to keep that in there. So the next thing is, I want to describe 2 different very simple concepts. One is called convex set. Convex set means if you have all the instructions in there. A convex set of instructions is if A and B instructions are in the convex set, instruction C is also a convex set if there's a path from A to B, execution path that actually has C in it. So while you're running from A to B, if you execute C also has to be in the convex set. So what that means is you can't have places, holes in the execution path. So if you get A and B, everything in that path, if it's reachable, has to be in the convex set. Does that make sense? What a convex set is? A set of instructions. And so minimal convex set of instructions that include all the defs and uses is basically the live range. What that means is basically all the definitions and uses has to be in the live range, instructions that do definitions and uses of that web. And then any instruction in the middle that passes through also has to be in the live range, because at that, intuitively it's a very simple concept. Because all the instructions, all the places of where you're executing, even though that instruction might not use the register, that value has to be live through that point. Because that's a definition, that's a use, and when you start executing from definition to use, everywhere you go, that value has to be kept live. At that point, you mark all the points that value has to be live using this convex set. So that defines you all the points that thing has to be live. Okay? So the next interesting concept is interference. If there are 2 webs, they interfere if the live ranges overlap. So what that means is there's a place somewhere that when you try to execute that instruction, both the value in the first web and the value in the second web has to be there, because either they use it or somebody later uses it, because both values have to be carried through. So what that means is those 2 webs interfere. And since I have to keep both values, I can't keep both of them in the same register. I can only keep one value. So here's a plane that you have to done. I have to keep both. I need at least 2 registers. Okay, so let's look at in this one. So where are the places where there's interference? Which webs interfere?
S1 and
S1 and S2 interfere. Yes, because so the convex set of S1 has this instruction, this instruction, this instruction, these three instructions. Okay. Convex set of S2 has this instruction, this instruction, this instruction, this, and this. So at least this instruction is in the convex set of both S1 and S2, and this also is in both S1 and S2. So because of these two instructions, I basically have interference in here. Actually, this is a good one. So this instruction, so there's interference, and also same here, S3 and S2 also there's interference. So these two webs interfere. Okay. So again, we trying to abstract and have a nice representation of that. It's called interference graph. So what that means is each web get a node, and each edge describes interference. So in here, what's my edges? S1 to S2, S2 to S3. I have those two edges, basically, with through interfere. So here's again, so now we have an elegant representation, and now the need for registers can be elegantly matched into a very nice theoretical problem, which is graph coloring problem. So register allocation using graph coloring says each web is allocated a register. Each register is a color. So assume I have 4 registers, I have 4 colors. So when each node gets a register, it gets a color. However, if 2 webs interfere, they can't have the same register. What that means is if I have an edge between 2 nodes, they can't have the same color. Okay, so this is a graph coloring problem. So I just mapped this very complex problem into a very nice theoretical problem. Now basically I have to go solve this graph coloring problem. Okay, so what basically now I had to do is I had to build this graph, interference graph. Now I need to assign colors to each node of the graph. And if 2 nodes have the edge, I can't have the same color. And this is a very simple problem. We mapped it to a problem, but the problem is not that simple. It's a NP-complete problem, but we have good heuristics. So we can actually get a really good solution. So can we always come up with a solution?
You have 5 or more colors.
No, because I might have a graph that will have, because that's 5 or more colors is assume a planar graph.
Right.
Okay, and there's no planar graph. You can have huge amount of edges in here. So if you have non-planar graph, I mean, it depends basically.
Yeah.
I mean, you can't always tell, and you can't even always tell because it's NP a complete problem to actually go even tell. So 1 color, easy. There's no interference edges in here. Okay. 2. Okay. Okay, so have you taken, where should you learn NP hardness? 6 over 6. Have you taken 6 over 6? Okay, so okay, we're now taking 6 over 6. So you learn it there. So what that means is most problems have a linear time solution or polynomial solution. That means you can say the time to take the solution has a polynomial equation in there. So it's n squared, n cubed, n whatever. NP complete means it's exponential. So that means you add one more thing to the problem, the size keep doubling. And so it's something in the computer science basically says this is kind of the limit of complexity. After that it becomes harder to compute because every time you just increase a problem by 1, time it takes doubles, and at some point it becomes very unwieldy. So most of the time, I think, at least classically, polynomial problems are something that you go brute force using. We know we can actually have n squared and you can solve that. People don't try to come up with easier solutions. But the minute we start hitting exponential problems, people just said, okay, that can't be done. So we'll have to come up with approximated solutions. In compilers, you have to be still careful though, because today's computers are so darn fast. Even for NP complete, even for exponential solutions, if n is small enough, you can probably do it. So you have to, it's just by saying it's exponential, you have to be think, okay, exponential on what? N is 10, 100, or 10,000. If n is 10 and 100, probably you can still do it today. if it is really important. So because computers are fast enough, that there was a time where a minute you say it's NP complete, you just say, okay, throw your hands and say, let me do something different. But today it's becoming a little bit more murky. So here we throw our hands and say, okay, so let me say, so it's 2 colors. How many colors here? 2. Can still do 2. Okay.
You can't really see a line.
Oops. Oh, darn. Sorry. Okay. Can you get the light? It's okay. I should have made it. Okay, yeah. Here. Oh, okay. No, this is good because I can see the lines very nicely. Okay. Oops, that didn't help. That I went. Okay. Now how much? How many colors? 3. Okay. Okay. So you have time to do a quick. Aha, this one actually do readable. Okay, good. So, okay. So, since it's NP complete, we come up with a heuristic solution. So what we want to do is color graph with n colors, number of registers. So if the degree, that means if you look at a node, if it has less than n edges going out, you can color the graph. So if every node has less than n edges going out, you can color the graph perfectly. Because that means what happens is if all the neighboring edges already have colors, okay, there might be n-1 colors. Okay, I already have at least have 1 color left to color myself. So I can never run out of colors. So so at that point you have a graph that's provably colorable. So if there's less than n, and so if there's greater or equal to n, there are some edges with some nodes with more than n edges, may be colorable, not sure. Okay, this is where the NP completeness come about. So there might be colorable, but we come up with strategy that we can actually find that. So what we do is we have come up with a very simple algorithm. The algorithm, see, most of the time what I try to do in my presentations is instead of giving you these very algorithms and say here's algorithm, I want to actually give an example to kind of give you intuition. Because algorithms are great, but I don't think you'll remember the algorithm, but if you at least get the intuition what's going on, it's better. So what you do is if it is, we look at all the nodes less than n, say I know I can color that. I will push them into a stack. And as I put some node into a stack, I eliminate the edges because that node, when the node goes, they just go. So at some point, you might get stuck because you put all the nodes into the edges, but all the nodes that are left, everybody has more than n edges in there. So at that point, we have to do is done. I can't color that subcomponent. Then I have to start removing nodes and say this node is not colorable. That means I have to spill that node. Until you find a graph, until you find some more nodes that have less than n edges, and you start doing that until you run out of all the nodes. So when you run out of all the nodes, you basically start popping things out of that stack. And every time you pop something, there should be a color available that you can color that. And you keep popping things out of the stack, keep coloring. Note that this can happen in a graph that has, at the beginning, has bunch of nodes that has greater than n edges. Okay, but the way if you keep popping the nodes at some point, because the minute I remove a node, edge also go away, I might be able to put all the nodes back in. So it's not that I'm just coloring a graph that has where all nodes have less than n edges. Some nodes might have greater than n edges. This algorithm will still do that, but still there might be cases that it might not. So here's a graph. Please, you can see the thing. So I want to do a 3-color this one. So is it obvious? I mean, can I just directly 3-color this one? I mean, the simple theorem is if every node is less than 3, I can. But here there are 3 nodes that actually 4 nodes that has 3 edges. So I can't really directly 3-color. But if you go about doing this algorithm, you will actually be able to color this. So what you do is first you find this node and say, aha, this node has less than 3, 2. So I can put that in there. I can now eliminate that node. And as soon as I eliminate that node, I found actually 2 more nodes that actually have less than 3. I can keep eliminating that. And now I have all 3 nodes have less than 3, and I can keep pushing those nodes into the graph. Okay? So I should put S0, so, but I didn't. But what that means is at the beginning I had a graph that is not colorable, but this heuristics let me color that graph too. So now what I do is now I pick my first node and say, okay, pick a color, put it there, and bring another node. I should have a color that I should color it, get a color in here. Bring another node, next node I should have a color in my color. I have the third color. What color goes here? Green, go here. And what color goes here? Blue or brown. So I can go there. So now I actually find the colors. It's a very simple algorithm. You can go, and it's in practice it will find for most cases. This one, on the other hand, can give you problems. So there, what happens is now I put this first one. I still don't have any nodes. Every node has more than greater than or equal 3 edges. So I can't take anything out. At that point, I have decided how to spill, because my algorithm now run out of options in here. And this is actually, in fact, it's not colorable, this graph even. So now I had to figure out an edge, and I said this edge I'm going to spill, and now I'm going to put the rest of it and then keep coloring, and I can basically keep coloring that. Okay? So now what happens is you came to a situation where you can basically, between spilling, doing spilling, you can actually come up with register allocation somehow there. So what's next? So now we have this thing. Now what do you do with these spilled webs? What do you do with that? We can do option 1, which is pick a web and allocate values in memory. So you can say, darn, now I can't, that I took that node, that name, and say this one I'm going to just put it in memory. So that means all def to go to memory, all users go to come from memory, and you might in fact have to increase instructions, because if you're doing operations that with 2 webs that's in memory, you actually have to add instructions in here. Option 2 is not give up yet and try to do other things like splitting web into multiple webs and stuff like that, to basically trying to make the graph colorable again. So can I do things to make the graph colorable? And in either case we have to recolor. So at some point we say, I'm spilling this, or I will change the graph and I'll create more webs, I will do some other transformations and try to recolor. So the key thing is which web to pick. Now I have a bunch of choices, so at least you have to pick something that has greater or equal to n edges. That's obvious. But what we want is we want to pick something that has a minimal spill cost if you want to spill that. And what that means is if you place that variable in memory, okay, what's your cost of doing that? And cost can come in many different things, because you might have additional instructions, or you might have more expensive instructions every time I use that thing. And there are extra load store instructions, and even the change you have to come up with a more expensive instruction. So ideal spill cost is trying to figure out the dynamic execution of both spilled versus unspilled, and say, okay, now if I dynamically execute with this in register versus spill, what's my cost? But this you can't do, because there are many things like branches you don't know, loops, how many times you execute you don't know. There's a lot of things you can't dynamically get the exact number. So what you need to do is to come up with some kind of approximation. The solution is some kind of static approximations. You can say, if you have a real compiler with profile information, you can use that and say, I know these branches for how much cost, but otherwise you can actually come up with a very poor man's estimation of the cost. So the poor man's estimations of the cost basically is so here's a very simple estimation. Every forward branch, 50-50. You have no idea where it's going. Every backward branch, which is loop, 1090 or 101. Because back loops means you keep around loops a lot. So backward branches go around a lot. But if the branches both are going forward, then it's some kind of condition 50, something like that. Just you can figure out. So you can say loops take 10 or 100 times in there. And the spill cost is basically you can look at the sum of doing that. I mean, the other way to do that is, so if you have unstructured graph, you can use those kind of computation and calculate to reach each point what's the probability with that. If you have a structured graph, you know every time you have a loop, you say, okay, that gets 100 times executed than something outside a loop. So if you know that the loop structure, you can actually get a much better estimate. So it's up to you when to do that. I mean, after you map, just bring the graph down and flatten it, you can do at that level, or when you have the loop information, you can calculate, annotate, and bring it down to. So up to you. And basically now what you want to do is choose the web with the lowest spill cost to basically do that. So in here, I know the loop structure, and what happens is spill cost for X is the store cost and load cost for X. Spill cost for Y in here is 9 times that, because that is inside the loop. That happens many, many times. So the moral of the story is, if you're inside the loop, you should not try to spill things that you access within the loop. And so that's a simple spill. Simple spill means in done, I have to select one for spilling. And now I go figure out a web. Hopefully that doesn't have accesses in the innermost loop. And that's a good web to spill. Okay, if you know the loop structure, that's a nice thing to do. So there's another things you can do. The other thing you can do is splitting. So the splitting means you have a web, and the reason you have this live range is the entire lifetime of the web you have to keep a value. How about if you split the web? And that means I divided that node into now 2 nodes, and by doing that, I might be able to get to a graph that actually become uncolorable, because now there was a node that has many edges coming in. Now you split it, and hopefully each will have less amount of edges coming into it because they interfere with different live ranges. So that's a nice thing to do. So here's a simple example. I have a loop in here, and I have 3 different live ranges. X and Y are only within that inner body, and Z goes all the way. And the interesting thing about Z is it's use and def at the beginning, and within the loop nobody uses it, and then only uses at the end. That's the best case scenario in here. And now if you want to do, so it's my interference graph. Everybody interferes with everybody else, so it's just a full interference graph. So you want to do if you have 2 registers, this is not 2 colorable. And so you have to do something. So what can you do? One thing you can do is split the web and say, so what that means is I keep within that region. So instead of saying one thing you can do is say, every uses of C, I am just going to use from memory. I'm not doing it. In here I said, okay, within that first region, I will keep it in register. So all the uses actually get registered. At the end of the region, I will put it into memory. And again, at the bottom, next region, I will get it out of the memory and keep it in the register. In here, the bottom is not that much of an issue because only one use. But if there are multiple uses, I use it from a register instead of again and again getting from memory. So because of that, I can minimize that memory access, basically. So here what happens is that the minute you do that, now we have 2 different, that got split into 2, basically. Z got is split into 2, one C1 and C2, and there's no that, and now I can 2-color this one. So I can have basically in here. So what happens is register R1 gets saved into the memory. So what that means is split web that gets split actually has a register allocated into each of them, and also has a memory location. Now because that web now actually has to be in memory at some point. So what that means is when you go from R1 to R2. Because when you go inside, start going into the loop, you actually have to put it in the memory location, and then R1 gets used for something else and come out of there. Okay, so you have to do the star and a load in here. Star and load. So what are the good places to split? So you need to basically find a place in the graph which is not colorable. Point in the graph that has more than, so that, and there, and then what you need to do is you need to pick a web, saying that for the largest region that's not being used. So and then at that point you will split that web and then redo the interference graph and try to recolor this thing. So the cost of splitting a node is every time you cross that the split point, you actually have to do a save and store from memory. So you're adding saves and stores from that thing. And it probably can be estimated by loop nesting. If you had to split inside the loop, every time the loop iterations, you had to go do that. The benefit is increase the colorability of a graph, splitting the web in interference graph. And this can be measured by the degree of interference graph. So basically, you better pick a web that actually is degree larger than n, because otherwise it doesn't help. You want to split that. And the benefit is, and also there's a cost. It depends on how many accesses within the innermost loop or place you want to split that actually this has. So you want to, nice thing is you want to find a way, if you have innermost loop somewhere that has interference that you have to split, you need to see whether you can find some webs where there's no access, there's just data going across that loop. And at that point, that's a good place to do that. And you can do a very simple greedy heuristic to do that, just basically. If you have a loop structure, you can just go do that. And let me talk about few more optimizations. So form optimization I want to talk about is register coalescing, register targeting or pre-coloring, pre-splitting the webs, and finally kind of current research topics like interprocedural register allocation. So assume I have a statement like that. Sj equal Si, somewhere, just simple assignment. And what happens is Sj and Si might have two different webs. We'll have two different webs because one is a use and one is a def. But since they are in a statement, they are not matched together. And in the compiler we generate a lot of code like that, and they might have two different webs that in fact doesn't interfere at all. Because the last use of Sj and the first last use of Si is there, and the first difference is Sj. So if you have two of these different webs, you can basically say just combine those webs together. Okay. Instead of having a bunch of very small webs, you can combine these webs. So the process now we basically did simple copy propagation in here. So copy propagation might have gotten it, but you can do that, and it basically reduces the number of instructions. You just got rid of that copy instruction because it's already in the register. Cons is you might have increased the degree by combining. So here's interesting thing. So before you run copy propagation, if you might have to have some notion about what happens, because if you do good enough copy propagation, you might ending up combining too many things, make a colorable graph non-colorable, because now you have much more overlapping webs. So this is where all those things, I mean, if you want to write a really good compiler, all those things have to come together. You say, okay, copy propagation is great, but hey, if you do too much copy propagation, I might run into problems. So this is a good optimization, but it's not always winnable. So you have to be careful in there. So other thing is register targeting. So here's the case where there are many variables that has pre-assigned registers. So if you're doing a call, if you're doing a full calling convention, there are a bunch of first arguments has to go into a bunch of very specific registers, return value has to go into a certain register, and there are a lot of these things. In the final one, what are we using your calling convention, or are we using the native? Okay, so if we are using native, this is it 6? 6. So there are if for 6 arguments has to go to some registers. So if you know that, if you don't deal with just in general, it might get into a different register, and then before you call, you have to copy. So you might as well say, okay, I know this variable has to be in register RX. I will start it there. I'll just pre-allocate that register because it has to be at the end of it, and I can eliminate the copy. And this can actually reduce a bunch of copying that needed. So allocate the registers in there. Okay, so the pre-splitting the web is basically also one thing you can do is the higher level pass before you go all the way down to unstructured graph. In your structured graph, you can look at variables that are live across loops but unused. You can basically mark it saying split these things, because I know I have this very large dead regions, and I can start just saying, okay, I know splitting this is better than anything else. And most of the times, breaking up will pay a very small cost, one save, but on the hand, you can make a graph that's much easier to color. So you can find very strategic place to break up, things like a call site. Where calls like you have to spill anyways. So you might as well break the graph and not have, because what happens, you have in the register, you spill it to memory and you bring it back to the same register, and you're paying the cost of having this live range by actually, you're already doing a save and restore anyways. So you might say, if you're doing call or save, you might as well break up in there. Around large loop nest, you might say, okay, around large, there's a large loop nest here, and if we are not using that value, I'm going to break up the thing. So you can start the question by saying, I'm not creating. So basically, you can set up something. I will never create webs around function calls. Okay, things like that. So that can make it easier. And then if you get few of those things right, then at the end of the thing, as a safety value, you will just spill things that you are non-colorable graph, because you'll get into a situation that you will have very rarely had non-colorable graphs, and you can spill anyways. And this if you actually do some pre-splitting. So then you don't have to get into a situation where you end up in a non-colorable graph, and at that point trying to go figure out where to split. You can just start with some pre-splitting, and actually go do register allocation, and if you find its graph is not colorable, just spill instead of trying to split. So you can come up with some strategies in doing things in register allocation in there. The final thing I want to talk to you about is inter-procedural register allocation. This is not something any of you guys will ever do for this project. It would be crazy to do that. And what that means is, because a lot of times what happens is, this calling conventions has a certain number of caller save and certain number of callee save registers. Certain number of things get passed as arguments. Okay? If we are not careful, what happens is there will be a lot of excess spilling, especially if you have a bunch of small leaf functions that use 2 or 3 registers, or 1 register or something like that. Since I have to do caller save, I will be spilling all those things, coming back, restoring, whereas that function never used them. Why do I spill? So what that means is, because the calling convention is too general. So one thing you can do is you can say, that function only used 1 register. On the other hand, I am using all the registers now, and I only need to spill 1 register to go there, because I'm not going to spill the rest of it, because I know it only needs that. So I can do a customized calling convention on each function, and basically get some reduced bunch of register communication. So you can do things like that. So there are interesting. So the other thing is, assume both functions have too many things, and all your arguments were in memory. And assume since I have to pass 6 arguments, I just take the 6 argument registers, pass it back, and immediately put it back into memory. Okay, why? And at that point, okay, if I know that I'm doing that, I can just say, okay, look, I will know the memory, I will tell you where it is, I don't have to give it in the register just to put it back in memory. Things like that you can do, but they are much more hairy optimizations, because what that means is you have to make sure that you have a custom copy that works for me, and if there's somebody else called that function, they have to get the different copy. It's too many complications, so I don't expect you to do that. The simple thing is, if you inline, you'll get all those benefits. You inline the code, and if you're doing custom copy, you're already paying the cost of duplication. Inline actually get you both register allocation and instruction scheduling and everything there. So it's probably better. So actually, if we are finishing a little bit faster. So in summary, so this is something we want you guys to do in the project. Register allocation basically stores values in registers between def and use, and really reduce the memory bandwidth. And it can have a big impact on performance. x86 64 will have some impact. On the other hand, if you go to architectures where RISC type architecture will have huge impact, because there most of the arithmetic operations happen. It's both the cost of memory operations as well as reduction of instructions. The key concept we did webs to basically identify regions, and we look at interference graphs to figure out what are the things that cannot be allocated in the same registers, look at colorability to figure out how to do that, and we talked about splitting. And this is basically the main thing. And I think for your project, you can probably get away with just doing webs, interference graph, and colorability, and then not worry about splitting and just spinning in there. Just probably need to keep 1 register for temporaries. You want to probably do pre-allocation. And if you are really gung-ho, you might be able to do some pre-splitting. And by doing that, I think you are pretty much set to do the project. One thing you have to be careful, though, is now that you might have to change your instruction mix too. So for example, if you if you have, if things are in registers, okay, you can do a lot of operation register operations in there. So if you have A equals A plus B, okay, then it's one instruction if both are in registers. If one is in register, still A equals A plus B is one instruction. But if both A and B are in memory, then it's two instructions. You have to load that. So you have to make sure that the way you generate instructions actually accommodate that, basically. So there might be, so here's where people optimizations come into play. So what you do is, you just keep generating this, you don't worry about that, you will get, because right now it's inefficient anyways, because everything is load to register, do operation, and the store type instruction. And then you create some patterns and say, if I find this pattern, I will combine it to the instructions. So you come up with this pattern matching people optimization. Then trying to do anything and go change everything. So if you say, if I find two things that is basically register to a copy into another register and operating on it, and say, okay, it can be combined together. So by doing things like that, you can actually, that's the best way to actually get rid of those kind of inefficiencies. And what I would say is, this is probably a good time for most of the codes, write a C equivalent, run it through GCC, all the optimization turned on, and see what it does. And see, and then look at your code and say, why it's not doing that? And some of it would be hard, because some of it GCC is doing crazy, outrageous things. You don't have time to do that. But some of it you'll find things to do. And if you are even more adventurous, you can play with different GCC optimization levels and see at what level that you can do, and turn on the optimizations that you can do at GCC, because it's all controllable in GCC, and see what you get, and see whether it's valuable. And then most of the time, run it, time it. Always put if you have a piece of code, put it through a very large loop, run it for 1,000 times, because so you don't have variability. Because most of the programs you have run so fast, and if you just time it, it's not useful. So run it for 1,000 times or 10,000 times, so you will get time in the. Run something for like 10 seconds, because everybody's in the same machine. If you run the same thing for a large loop and run for an hour, it doesn't help you. I mean, if you get a timing around 10 seconds of a program, that's probably reliable enough. You probably got rid of all the noise. And also, since there are multiple groups using the same machine, if you're timing, just do a top or something and see who's running. And if everybody's trying to time at the same time, you might get different types. So what I would do is I would put a loop around the things you're testing, that make sure that it runs for about 10 seconds. Run it for about 2 or 3 times and make sure it's repeatable. So if it is not repeatable, that means something is going on, some other people are using the machine, look at the load. You can send people messages trying to, if we run into issues of everybody's having hard time getting timing, we can come up with some way of allocating few minutes here and there, so people get a machine. But Punna, is that it's not a 2 process, isn't it? What you got? It's a 1 processor, 2 thread machine, isn't it?
I'm not sure.
I think it's a 1 processor, so I can't remember that I ordered a 2 processor for that. But I think for most of the time, you guys are not running large programs. But here's the time now you can actually time it, get feedback, and then figure out what right thing to do. So what we are doing for the project is we are giving only one thing mandatory to do, register allocation. And the rest, Pune is going to give you some loops. And you guys figure out what best to do. And this seems like easier thing to say, but it's much harder thing to do, because x86, lot of times intuition is hard to come by, because it's a very complex architecture. So things you think, oh, this should give good performance, probably hardware already does something, you won't get it. It's a dual core single one processor. Okay, yeah. So that means 2 people can run. You won't get the interference at the same time. But it's always good to check who's out there, who's running. Or send a message to the entire people logged in the machine and say, I'm next 5 minutes I'm doing some tests. So just you have to don't run into each other and get mad. But I think with these few groups, you should be able to do it. I mean, it's not like you are benchmarking for hours. So use the same machine. Good. So 1 more lecture and then the derby. That's all that's left. And 1 more project. Almost there. Huh? Oh, there's a quiz too, yeah. Small details.